about it. Specified complexity. Turns out in our DNA we have what's called specified complexity. You guys use a design inference all the time. And let me show you an example. This license plate has specified complexity, okay? Or sorry, has complexity. This license plate here has specified complexity. Imagine on my birthday, I'm given a car, okay? My wife buys me a car. Maybe it's an old Galaxy, 60 whatever, and Ford Galaxy. And it says, the license plate says TIM, my name's Tim, and the year I was born, 1983, okay? Now, I could say, well, you know, someone had to get that license plate, and it's just lucky I did. Because it turns out the actual complexity, the probability of getting these two license plates is actually the same. You can calculate the probability, and it's about 1 in 167 million, okay? Same probability. But here's the difference between complexity and specified complexity. Specified complexity fits an independently given pattern. So it would be ludicrous for me to say, well, all license plates are equally complex to get, and it just so happens I got this one by chance. No, I'd be crazy to say that. It's because it fits this pattern, okay? And so there's a difference between these two. And it turns out when you look at the DNA molecule, it has what we call specified complexity. Bill Gates, not a biologist, but he recognized it. He says, DNA is like a supercomputer. He understands software, but far, far more advanced than any software ever created. And a lot of these guys are comparing DNA to software now. The problem of the origin of life is clearly basically equivalent to the problem of the origin of biological information. They can't explain where life came from, and one of those reasons is because it has this information built into the system. So scientists have discovered that the DNA double helix structure is has specified complexity. What do I mean? Well, here we have the English language has a code system. It has 26 letters in its alphabet. The DNA molecule actually has its own code system, okay? Made up of nucleotide bases, which we give the letters G, C, A, T, okay? So just like this has A to Z, this has a 4-letter alphabet. And when you put these letters in order, in a certain order, they actually spell out, there's a codon here, every 3. And that's going to code for amino acids, and amino acids codes for protein. If you don't know this, take biology. You guys need to. This is really cool stuff. And so, like, my kids are loving it at school right now. And and if you actually move one of these letters, you delete it, like a point mutation, a deletion, or you insert a letter, or if you delete a whole section, then you screw up the whole thing. Okay, this is bad news. This is what mutations do. So you could imagine an article in a newspaper, someone just putting a letter in at some point. And the meaning gets kind of screwed up. But you and your brain, you're using, okay, they made a mistake here. And so that's what mutations do. And so it turns out there's specified complexity, a certain pattern here that's necessary for life.